In this presentation, we will be discussing pouring concrete underwater, presented by Carly Beecroft, Richard George, Riley Stewart, and Jesse Postnikoff.
So a quick agenda that we have here for you today. We're going to talk about the challenges of underwater concreting. We're going to talk about practical applications, methods of placement, ideal mix design considerations, guidelines of underwater mix design, admixture benefits, industry examples, recommendations, and finally a short question period. Some of the challenges of underwater concreting are washout, segregation, flowability, compaction, cohesiveness, and pore monitoring. These are things that we're going to be talking about throughout our presentation to show you how concrete pouring underwater can be much more difficult and have its own rewards. Some practical applications, the things that you would use underwater concreting for would be things like pipe enclosures, bridge piers, dry dock wells, dry dock walls, structural anchors, dams, and caisson seals. Next, we're going to be talking about the methods of placement. The three main methods of placements for us today are the Tremy method, the bucket method, and the free fall method. Starting off, the Tremy method of placement, what it is exactly is it's a 250 millimeter diameter pipe, roughly from the bottom of the excavation inside, and that is lowered into the water or some other sort of formwork that you've created underwater, generally with all the way to above the surface of water, and release the bottom of it. A hopper at the top to ensure that the concrete goes into the pipe bucket and there's no extra waste. Then you can remove the bucket. The beauties of the Tremy method is that you're going to be minimizing contamination and segregation because it's a closed system. I'll explain in a second how there's two different Tremy methods, depending on the size of it and wet method. We'll get into the last method, of course, generally what's happened method. This is something that isn't as prevalent yet in the industry. At the top, which will just came about recently, based on technology advancements, Tremy pipe and into your formwork to control the properties. It's a little bit of setup work, but it pays off in the long run. And this is generally done in shallow water at this time, and they're looking at ways to expand it into bigger concrete pours and making it more cost-effective to pour concrete underwater. The most used method here is the Tremy method. The two main types of pours in the Tremy method is the dry and wet. The major difference is one has a plug at both ends, while one has plug only at one end. And the dry method will make sure that the entire Tremy pipe itself will stay dry the entire time until the concrete flows into it. Whereas the one other method is only to separate the water inside the pipe, let it fill completely with water, separate the water that's in the Tremy pipe, and then the concrete in there between a plug. And as the concrete pours, in both methods, it'll push the plug or plugs through the Tremy pipe and then into the formwork and out of the formwork, while the formwork will fill with the concrete. In the wet method, the water will remove through the formwork before the concrete falls through and into it. The concrete will obviously be heavier and more dense and will fill the space created by the concrete form. So if you decided to use the Tremy method in one of your next concrete pours underwater, the main steps that you would take is you would build, place, locate, pour, test, and deconstruct. I'll walk you through each step briefly. So you'd build the formwork, you'd decide what concrete structure you're going to be building underwater, and build a wooden or steel formwork in order to house that concrete. Then you will place the formwork in the water exactly where it needs to be. Then you will locate your Tremy pipe within that formwork. After that, you will then pour the concrete through your tremie pipe and your tremie system. You will test to make sure that the formwork is adequately filled, and then you will wait for it to cure. You'll deconstruct your tremie pipe in the process, and you will end up with a finished full mold of underwater poured concrete with the desired size, requirements, and strength capabilities required for your project. Second most used technique for pouring concrete underwater. The main thing is that you'll always have an underwater diver with that bucket underwater, so you'll be able to tell anytime there's any contamination or leakage. If your bottom jaw is not strong enough or your roller gate is not closed properly, you'll see it as soon as it reaches into the water. The diver will guide that bucket along with their rope that's holding it in there down into the formwork. Then they will release that bottom jaw either through a hydraulic, air pressure, or through some other form of mechanical system. Even a roller gate would work as well and is very popular in the industry. The jaw will release, open, the concrete will flow out of the bucket and into your formwork. Then you'll be able to roll the bucket back out of the water.
Here you will see a chart mapping out the ideal mix design considerations and how they influence each other. There's ingredients, properties, and characteristics, as well as requirements. Here you will also see how all the characteristics and aspects of mix design influence each other. Guidelines of underwater mix design. A dense gradation curve is most effective along with a 10 mm maximum aggregate size and 40% minimum fine aggregate content. 15 to 20% should pass through a 0.315 mm sieve, which is necessary to enhance the cohesive properties of the concrete. Rounded aggregate achieves a more dense packing and have reduced water demand for a given degree of workability than do crushed rocks. Rounded aggregate generally tends to increase cohesion for a given sand friction and cement content, which results in a reduced tendency to segregation and bleeding. Self-consolidating is necessary as the mix must spread and merge under its own weight. For most cases, mechanical consolidation or a vibrator cannot be used. Because of the buoyancy of the water, the weight of the fresh concrete is reduced. Therefore, a slump value of greater than 175 mm is required. The mix must be cohesive enough to counteract the effects of washout bleeding and segregation. Increasing cohesion has an inverse effect on the flowability of the concrete. Admixtures are added to the mix to counteract these problems.
Next, we are going to talk about admixtures and their benefits to underwater concreting. Admixtures are an emphasized part of mix design as they alter the properties of the mix and help it perform in certain conditions. 4 admixtures in particular that we will talk about are water reducers, fly ash admixtures, silica fume admixtures, and anti-washout. Water reducers are commonly used admixture in underwater and normal concrete practices. The main purpose of water reducers are to reduce the water present in the mix. Therefore, this decreases workability and increases strength. By decreasing workability, you are also reducing the chance of possible segregation in underwater concreting. Water reducers are mainly composed of salts, different types of acids, and carbohydrates, and are generally found in liquid form. Fly ash is another commonly used mix design component. Fly ash is a cementing material with different properties than that of Portland cement. It has a smaller particle size and therefore has less voids in the mix when it's present. This allows for decreased permeability, which is very important in underwater concreting, as it does not allow water to penetrate the mix as easily. It also leads to higher strength in the mix, which is another important component. Silica fume is another cementing material with similar properties to that of fly ash. It allows for decreased permeability and increased strength in the concrete. In addition, it can help lower the cost of your mix. It also helps to increase cohesiveness in the mix, which is important in underwater concreting. With the main issues being segregation and washout, increased cohesiveness helps to counteract it. The last admixture we're going to talk about today are anti-washout admixtures. Anti-washout admixtures are commonly used in underwater concreting and are made by various different companies. Although you can use water reducers, fly ash, silica fume, and anti-washout in different combinations in your mix, we feel as anti-washout admixtures are the most essential for underwater concreting. They help to prevent segregation and increase cohesiveness like silica fume. They also are essential in ensuring that the placement of the concrete works. They help to self-compact the mix and help to stabilize the concrete while it's being pumped underwater.
Underwater concreting and the methods, mix designs, and admixtures associated with it have continued to be developed and refined to create a concrete that meets the unique requirements for underwater applications. As a result of the increased performance, there are more and more applications for underwater concrete. What is still needed in the field is a comprehensive set of tests and standards designed specifically for pouring concrete underwater. Currently, standards are in-air tests such as the slump test, and can only give a non-complete understanding of the concrete's characteristics once introduced to the water. The lack of standardized tests and practices increases the risk of substandard mixtures and resulting concrete performance. Thank you, and we will now take any questions.